For decades, nuclear fusion has remained a tantalizing vision, perpetually just beyond our grasp. Often described as always 20 years away, it is easy to view this technology with skepticism, especially given the existing, yet underutilized, power of nuclear fission. However, the potential impact of harnessing fusion energy is so profound that it demands our continued attention and excitement. Should humanity succeed in developing a cost-effective nuclear fusion power plant, the fabric of global society would be irrevocably transformed. Imagine a world powered by clean, safe, and virtually limitless energy. Such a breakthrough would enable every nation to achieve true energy independence, eradicating one of the primary drivers of international conflict, the struggle for control over vital energy resources. Abundant, cheap, and reliable energy forms the very bedrock of the utopian societies frequently envisioned in science fiction. It promises a future where climate change is addressed, where energy-intensive industries like steel smelting can be electrified, and entirely new sectors, previously constrained by energy costs, can flourish. Water desalination, for instance, could provide fresh, clean water on an unprecedented scale, transforming barren lands into fertile pastures. This is the promise of fusion, an era of clean, safe abundance, a dream pursued by humanity for generations. The pursuit of nuclear fusion energy began in earnest during the earliest years of the Cold War. By the 1950s, both American and Soviet scientists were conducting pioneering experiments. The Soviet Union gravitated towards the Tokamak design, while American researchers explored the stellarator. Both approaches aimed to solve the same fundamental challenge: how to achieve sustained nuclear fusion. At its core, fusion is a process of combining lighter atomic nuclei to form heavier ones, releasing immense amounts of energy in the process. However, forcing atomic nuclei to merge is far from simple. Like attempting to push the north poles of two powerful magnets together, atomic nuclei naturally repel each other due to their electromagnetic charge. Overcoming this powerful repulsion requires an extraordinary input of energy. Instead of manipulating individual atoms, scientists create a plasma, a superheated cloud of charged ions. Due to their electrical charge, these ions can be controlled and confined by powerful magnetic fields. This magnetic confinement prevents the incredibly hot plasma from touching the reactor walls, which would otherwise melt instantly. The plasma's temperature is then gradually increased to extreme levels, causing the ions to accelerate to such speeds that the kinetic energy alone is sufficient to overcome the electromagnetic repulsion, allowing them to collide and fuse. Both the Tokamak and stellarator designs employ massive superconducting magnets to generate these confining magnetic fields, albeit with slightly different configurations. The Tokamak design gained prominence after 1968, when information released by the Soviet Union demonstrated a significant leap in its energy efficiency, establishing it as the leading design in fusion research. Regardless of the reactor design, the choice of fuel is critical, as it profoundly influences both the energy input required and the energy output achieved. Most fusion reactions utilize two isotopes of hydrogen, deuterium and tritium. While it is theoretically possible to perform fusion with ordinary hydrogen, which has a single proton in its nucleus, the energy yield from such a reaction is very low. Deuterium, however, possesses one proton and one neutron, while tritium has one proton and two neutrons. This deuterium-tritium (DT) combination is favored for several key reasons. Firstly, it offers the highest probability of yielding the desired fusion outcome. Other reactions, such as hydrogen-to-hydrogen fusion, have a high likelihood of producing unstable helium-2, which quickly decays back into hydrogen with minimal energy release. While the Sun performs a complex chain of hydrogen fusion reactions, it relies on an unfathomable quantity of particles and immense gravitational pressure, conditions impossible to replicate on Earth. On Earth, we must supply the necessary particles and the energy to fuse them ourselves. For fusion to be a viable energy source, the energy extracted must significantly exceed the energy input. Significant progress has been made in achieving fusion on Earth. Scientists have successfully created numerous fusion reactions, demonstrating our understanding of the fundamental process. The current challenge lies in optimizing these reactions, minimizing the energy required to initiate fusion while maximizing the energy extracted. This is precisely where deuterium and tritium excel. When these two isotopes combine, they have a high probability of forming helium-4, releasing an average of 17.6 megaelectron-volts, MeV, for each fusion event. To put this in perspective, while a single uranium-235 fission event produces 11.4 times this energy, a DT fusion reaction releases over 4 times as much energy as uranium fission on a mass-for-mass basis. Crucially, DT fusion produces no dangerous, long-lived radioactive waste products. The helium byproduct is, in fact, quite useful, finding applications in cooling superconducting magnets for MRI machines and as an inert gas for rocket tanks. Furthermore, as global reserves of helium are finite, having a means to produce it ourselves could prove beneficial. Deuterium is relatively abundant on Earth, naturally occurring in seawater and comprising approximately 0.02% of the hydrogen present. Its extra neutron makes deuterium-containing water molecules heavier, hence the term heavy water. This density difference allows for its separation using various methods, such as vacuum distillation, which exploits heavy water's higher boiling point, or the Girdler sulfide process, which uses chemical reactions. Once separated, the heavy water can be electrolyzed to extract pure deuterium. The scarcity of tritium, however, presents a significant hurdle for nuclear fusion. Our primary current source of tritium is the moderator pools of nuclear fission reactors, particularly those that use heavy water. These pools are designed to absorb high-energy neutrons released during fission, and in doing so, some of the heavy hydrogen can be transmuted into tritium. Unfortunately, this source is becoming increasingly limited as older nuclear power plants are decommissioned globally due to economic competition from other electricity sources. Current global tritium reserves are estimated at a mere 20 kilograms. To illustrate the severity of this shortage, a large-scale international fusion experiment under construction in France estimates that a commercial reactor would require 300 grams of tritium daily to generate 800 megawatts of electrical power. At this rate, the entire global supply of tritium would be consumed in just over 2 months. Even if fission reactors continue to operate, they only produce about 100 grams of tritium annually, which is far from sufficient. Fortunately, a solution for tritium scarcity is being developed, on-site breeding within the fusion reactor itself. The high-energy neutrons emitted from DT fusion reactions, being magnetically neutral, can be used to perform a kind of nuclear alchemy. When these neutrons encounter lithium, they can split the lithium atom into tritium and helium, providing a continuous supply of tritium precisely where it's needed. This process occurs in a blanket that surrounds the fusion chamber. The design of this blanket is one of the most intricate and challenging aspects of Tokamak fusion generator engineering. The International Fusion Project in France, for example, will test over 180 design variants for the blanket that will line its donut-shaped interior. The blanket must fulfill multiple critical functions beyond tritium breeding. It is also where the kinetic energy of the fusion reaction's neutrons is converted into usable heat. Approximately 80% of the energy released in a deuterium-tritium fusion event is carried away by these high-energy neutrons. As the fusion reaction rages in the plasma core, neutrons erupt outwards, unaffected by the magnetic confinement. Tokamaks convert this energy by slowing the neutrons down within the blanket material, transferring their kinetic energy into heat. This heat is then captured by high-pressure water circulating through cooling channels, converting it into high-pressure steam. This steam then drives a turbine to generate electricity, using humanity's well-established method of power production. The material chosen for the blanket must possess unique properties. To optimize both heating and tritium breeding, it needs to be a neutron multiplier. When a high-energy neutron from the fusion reaction enters the blanket, it ideally strikes an atom within the blanket and releases 2 asterisk neutrons, ensuring that the blanket can generate heat and produce tritium simultaneously. Beryllium is currently a leading candidate for this role. When a neutron strikes beryllium, it splits into 2 helium-4 atoms and 2 neutrons. Beryllium is favored because its helium byproduct does not contaminate the plasma, and, crucially, it retains very little tritium, allowing the gas to be efficiently collected for fuel replenishment. However, beryllium also presents significant challenges. The sheer quantity required for a commercial fusion reactor, estimated at between 216 and 560 tons, is problematic. Beryllium is extremely expensive due to its limited global supply, which amounted to only about 260 tons last year. This means the entire annual global supply of beryllium would barely be sufficient to build one such reactor. Furthermore, there are safety concerns. Beryllium can contain trace amounts of uranium. If a beryllium blanket module contains, for example, 100 parts per million of uranium, meaning 0.01% of the blanket is uranium, this becomes a major issue. When this uranium is exposed to the high-energy neutrons from the fusion reaction, the very same type of neutrons that drive fission reactors, it creates fissile isotopes, effectively making the beryllium radioactive. A commercial-scale fusion reactor with just 30 parts per million of uranium in its beryllium would contain 17 kilograms of natural uranium and 123 grams of uranium-235, the isotope critical for fission. The radioactive byproducts generated would make the disposal of the blanket at the end of the generator's life incredibly complex and costly. These challenges highlight a fundamental concern with the current Tokamak fusion reactor designs: cost. Even if net energy output is achieved, these generators may not solve the biggest barrier currently hindering nuclear energy's broader adoption: economic viability. Nuclear fission power, a marvel of the last century, promised abundant, clean, and cheap energy. Yet, despite its environmental benefits, fission reactors are being decommissioned globally because they are often uneconomical. The exorbitant cost of construction and the complex, expensive process of managing radioactive waste during decommissioning are the primary factors. Many tokamak designs appear to be heading down a similar path, facing comparable economic obstacles. Recognizing these challenges, some innovative organizations are exploring fundamentally different approaches to nuclear fusion. These alternative strategies aim to bypass the limitations of current designs. For instance, some are developing methods that eliminate the need for costly steam power cycles and the problematic beryllium blankets. Others are devising ways to produce tritium fuel on site, not from lithium, but from the more readily available deuterium, reducing dependency on a scarce resource. Still others are pioneering entirely new magnetic confinement techniques to achieve the necessary fusion temperatures. These diverse research avenues underscore the dynamic and evolving nature of fusion science, as researchers strive to overcome existing barriers and unlock fusion's transformative potential. In conclusion, nuclear fusion remains humanity's grand ambition for a limitless, clean energy future. While significant scientific progress has been made since its inception in the Cold War era, considerable engineering and economic hurdles persist. The scarcity of tritium and the complexities of blanket design, particularly concerning materials like beryllium, present formidable challenges. Furthermore, the imperative to achieve not just scientific success but also economic viability is paramount. Despite these obstacles, ongoing innovation and diverse research approaches offer hope that the dream of clean, safe, and abundant fusion power, a true cornerstone of a utopian society, may one day become a reality.